Hi, and thanks for joining me for Tutorial 8. In Tutorials 5 and 6, we went over how we can use the getOR function to estimate odds ratios and their associated 95% confidence intervals from a logistic regression model. And you can see this in the tutorial R code. But remember that we can't simply use the getOR function to get odds ratios when we have an interaction term in our model. We need to do the calculations by hand, like how we learned in Tutorial 6. In this tutorial, we'll again go over how to calculate odds ratios by hand when you have an interaction term in your model. But unfortunately, there is no simple way to calculate 95% confidence intervals for odds ratios in R or by hand when an interaction term is present in your model. So for assignment 2, you are not expected to include 95% confidence intervals for strata-specific odds ratios if you decide to include one or more interaction terms in your model. For the assignment, it's completely acceptable to calculate the strata-specific odds ratios and then guess whether or not you think these are significant. If an odds ratio is close to 1, then we could guess that the 95% confidence interval will probably include 1. So it's probably safe to assume that this is not significant. You could also fit stratified models to calculate confidence intervals for the odds ratios. So, for example, if you found that there was a significant interaction between education and wanting more children in assignment 2, you could fit one model restricted to the subsample of participants who want more children, and another model for those who don't want more children. You could then get the odds ratio and confidence interval for the education effect within each of these two groups. But you don't have to do this for the assignment. There's no need to calculate or report confidence intervals for strata-specific odds ratios on the assignment. You can just guess whether these are significant or not. But if an odds ratio is close to 1, it's most likely that this is not significant. So now we're going to summarize and wrap up logistic regression. By the end of this session, you should be able to run logistic regression in R and interpret output from logistic regression, including coefficients, odds ratios, and their confidence intervals. You should also be able to compare models statistically, know how to assess confounding and interaction, and make predictions of log odds, and probabilities based on your output. You should know the difference between predictive and effect size models and how to check linearity with logistic regression. In the remainder of the tutorial, we'll review why we use logit and how to calculate and interpret strata-specific odds ratios when you have one or two interaction terms in your model. We'll also discuss some resources for learning more about the Mantel-Haenszel method and how to check linearity with logistic regression. And finally, we'll review how to estimate the probability of an outcome with logistic regression. Remember that when we have a binary outcome, we need to use the logit transformation. This is because the relationship between x and the probability of a binary outcome is not linear. It has more of an S shape. We want this to look like a linear function, so we use the logit function to link our nonlinear model to a linear model. This allows us to fit the log odds of a binary outcome as a linear function of the x's. Looking at the log odds is helpful because it gets us on the scale of a linear function, so it allows us to fit a line. We want to get on the scale of the linear function because lines have nice simple properties. Fitting a line gives us a slope, which has an easy interpretation. With the initial S shape, we can see that the slope varies for different values of x. But when we transform this using the logit function, the slope is constant. It's the same at each point along the line, so it makes our interpretations much easier. This slope tells us how the log odds of y change with each increase in x, and this is consistent everywhere along the line. So rather than modeling the probability of the outcome as a logistic function of the x's, we use the logit transformation, which allows us to model the log odds as a linear function of the x's. Recall that when we add interaction terms to a model, we're asking whether the effect of x1 on y varies or depends on a third variable, which is the effect modifier. Also recall that to first determine if the effect of x1 on y is modified by this other variable, we add the interaction term to the model and conduct a likelihood ratio test, which is equivalent to the partial f-test with linear regression. And this allows us to determine whether the interaction term significantly improves the model by reducing the residual deviance. If it does, then it can be said that x2 is an effect modifier. This implies that the effect of x1 on y depends on x2. In other words, the effect x1 has on y differs for different levels of x2. So now that our interaction term is significant, how do we calculate the odds ratios for each group? As I previously mentioned, we cannot simply exponentiate our coefficient for the interaction term or use the get-OR function in R to get the odds ratios. The exponentiated coefficient for the interaction term does not represent an odds ratio. This mistake is often made because stats programs like R will report the odds ratio as the exponentiated coefficient, whether or not these represent a true odds ratio. So let's turn to an example with an interaction term where we're wondering, does the effect of smoking on CHD depend on if you drink alcohol? Smoking and drinking alcohol are both binary, yes versus no, while age category has 3 levels. To be completely transparent, this data is not real. It's made up, but it can be difficult to find significant interaction terms, and I wanted to show you how to calculate strata-specific odds ratios, so let's just pretend this is real for the sake of discussion. Okay, so let's say that we've conducted a likelihood ratio test and found an interaction term between smoking and drinking alcohol significantly improves the model. This suggests that the effect of smoking on CHD depends on whether or not you drink alcohol. The association between alcohol and CHD is different for drinkers and non-drinkers. Recall that the exponentiated beta 1 gives us the estimated odds ratio for x1 adjusted for other variables in the model. When an interaction term is in the model, we must be careful when interpreting this effect. If you had this data on an assignment and you found this significant interaction between smoking and drinking, and you were asked, what's the effect of smoking on CHD? You can't just interpret the effect of smoking by exponentiating 0.35 to get the overall odds ratio for the whole group. This is because we've determined that the effect of smoking depends on drinking. As I've mentioned in previous tutorials, if an interaction term is significant, we should only interpret the effect of smoking on CHD in each stratum of the effect modifier. In other words, we should report one odds ratio for drinkers and another for non-drinkers, not an odds ratio for both non-drinkers and drinkers combined. This is because we've determined that the effect of drinking differs for smokers and non-smokers, so it doesn't make sense to report an odds ratio summarizing the effect for these groups combined. So how do we calculate the strata-specific odds ratios? In other words, how do we determine the effect of smoking on CHD for A, those who drink, and B, those who do not drink? First, let's look at the drinkers stratum. Recall that we calculate the log odds ratio by dividing the odds of CHD for smokers who drink by the odds of CHD for those who don't smoke but drink, and then taking the log of this. Since we're working with logs, this is actually mathematically equivalent to subtracting the log odds of CHD for those who don't smoke but drink from the log odds of CHD for those who smoke and drink. Working with this second formula, we can determine the odds ratio for the effect of smoking among drinkers. This allows us to work directly with our output to calculate the odds ratio. I'm now going to show you how to use this formula to calculate the strata-specific odds ratio for drinkers and for non-drinkers. This is the long way, but it's a good way to learn it, and then as you practice more, you won't have to use it as much. The strata-specific effect should become more intuitive. So I would suggest that you write out the full log odds equation for smokers and non-smokers within each level of drinking. You probably won't need to do this each time once you get used to calculating and interpreting strata-specific odds ratios, but I think it's a good way to learn it. So let's start with the drinker stratum. The top part of the equation tells us the log odds of CHD given that you smoke and drink. The bottom part of the equation tells us the log odds of CHD given that you don't smoke but drink. As we've done previously, we multiply each coefficient by 1 that relates to membership in that specific group. So for those who smoke and drink, we assign a value of 1 to any coefficient that includes smoke or drink. For those who don't smoke but drink, we assign a value of 1 to the coefficient for drink and a 0 for each coefficient that includes smoke. We can see that this gives us a value of 0 for our interaction term, since 0 times 1 equals 0. So now that we have the full equation, we can insert our coefficients from our output into the equation. Once we've done this, the next step is to compare the log odds equations for the smokers and non-smokers. We'll want to scratch out everything that equals 0, or is the same, comparing the log odds for smokers and non-smokers, and therefore cancels out. So once we've done this, we're left with a log odds ratio for smoking, given that you drink, of 0.35 plus 0.43. This makes sense conceptually if you think about it. Within the drinkers group, the only thing that differentiates the odds of CHD for the smokers and non-smokers is whether or not they smoke. And since only smokers are assigned a value of 1 for the interaction term, and non-smokers are not, the smoke and smoke times drink interaction term are the only two coefficients that differentiate smokers from non-smokers. In other words, the drinker's specific log odds ratio is 0.78. Among drinkers, the log odds of CHD are 0.78 higher for smokers compared to non-smokers, adjusting for categorical age. If we exponentiate this, we get an odds ratio of 2.18. We follow the same process with the non-drinking stratum. Among non-drinkers, the log odds of CHD are 0.35 higher for smokers compared to non-smokers, adjusting for categorical age. If we exponentiate 0.35, we get an odds ratio of 1.42. If we wanted to know if this is significant, we can simply look at the p-value associated with the smoke coefficient, which is significant. We could also use the standard error associated with this coefficient to calculate the confidence interval. Remember that the confidence interval is calculated as 2 times the standard error for the smoke coefficient. But with our previous example, among drinkers, when our odds ratio calculation is based on 2 different coefficients, we cannot simply multiply the standard error of either or both of these coefficients by 2 to get our confidence interval. This requires incorporating the estimated covariance of the 2 parameters, which is not available from our output or possible to do in R. So again, you are not expected to calculate confidence intervals for strata-specific odds ratios for this assignment or for the course. If you really wanted to get 95% confidence intervals for your strata-specific odds ratios, you could fit stratified models. In this case, you would fit 2 separate logistic regression models, one for drinkers and one for non-drinkers, and then use the get-OR function in R to get the odds ratio and 95% confidence interval for the smoking effect in each group. The odds ratios and confidence intervals would be slightly different than our model with an interaction term, but very close. That being said, you are not expected to do this for assignment 2. So now that we have our odds ratios from our example, how do we interpret these? We would say that among drinkers, smokers have 2.18 times the odds of CHD compared to non-smokers, adjusting for categorical age. And among non-drinkers, smokers have 1.35 times the odds of CHD compared to non-smokers, adjusting for categorical age. So we found that the effect of smoking varies depending on if participants drink alcohol. But does it also depend on age? Again, this data is made up, but I'll just use it to show an example. Let's say we conduct a likelihood ratio test and find that the smoke times age category interaction term is also significant, in addition to the significant interaction between smoke and drink. This suggests that the effect of smoking not only depends on whether or not you drink, but also on your age. So now we would have 6 strata-specific odds ratios that we would need to calculate. There will be 3 age category specific odds ratios comparing smokers versus non-smokers within the drinking stratum, and 3 age category specific odds ratios comparing smokers versus non-smokers within the non-drinking group. Let's try an example. Let's say we're interested in the effect of smoking among drinkers in age category B. We follow the same steps as before of writing out the full equation for smokers and non-smokers in this category and assigning 1s and 0s as appropriate. We then scratch out whatever equals 0 or cancels out, comparing the log odds for smokers and non-smokers. We can see that we're left with the smoke coefficient and the smoke times drink coefficient, and the smoke times age category B coefficient. Again, this makes sense because these are the only coefficients that differentiate smokers from non-smokers in this category of drinkers in age category B. All of these coefficients include smoke, which is what differentiates smokers from non-smokers in terms of effect on CHD. If we follow the same approach with non-drinkers, in age category C, the only coefficients that differentiate smokers are the smoke coefficient and the smoke times age category C coefficient. So we would add these together and exponentiate this number to get our odds ratio of 2.08 for this group. I'm not going to go over all of the strata-specific odds ratios because this would take a lot of time. But if this is something that you're struggling with, you could try practicing calculating the odds ratios for the other strata in the table to see if you get the same answers. Another method that I won't go over today due to time constraints, but you should read up about, is the Mantel-Haenszel method. This method allows us to control for confounding through stratification. A couple of drawbacks of this approach is that you cannot use it with continuous variables, and it's labor intensive. Some good resources for learning about this method are the SPPH 503 textbook and this article from Nephron Clinical Practice. Okay, so let's return to our model from tutorial 6. This is the model that we had decided on when analyzing the effect of smoking on CHD. Let's say that we've decided that this is our final model. The next thing that we need to do is check our model assumptions. The first assumption is that Y values are independent, which requires knowledge of study design. The second assumption is that Y is distributed binomially given X. We don't need to check this because if we have a binary outcome, therefore Y is binomial. The third assumption is that the expected Y is a logistic function of the X's. In other words, the relationship between the log odds of Y is linear with the X variables. We need to check this assumption for all continuous explanatory variables. The fourth assumption is that the X's are fixed values, meaning that they do not change, which we know through knowledge of study design. And the final assumption is that the model fits well, which we've learned that we can examine with methods like the likelihood ratio test or AIC. But linearity is the main assumption that we need to check statistically. So we need to check for linearity between all continuous explanatory variables and the log odds of y. There are a couple of options for checking linearity. The first is to divide the continuous explanatory variable into several groups. How you divide the variable into groups will depend on the number of observations, but quartiles is often used. You can then calculate the proportion with the outcome in each category. Next, you convert this proportion to log odds and plot this to see if it looks linear. The points should fall on a line. The other option to check for linearity is to compare a model with x versus a model with x and a higher order term such as x squared or x cubed. Or you can transform x. For example, you could try logging x. You can then check the model with the higher order term or transformed x to see if this addresses the problem. But the issue with this second approach is that it won't capture every type of nonlinearity. For example, if you include x squared, you will only catch quadratic curve linearity. So you can miss things. So the first option to check linearity may be better to understand the relationship between x and y. And then you can try to use these kinds of transformations to address any problems with linearity that you might have. Remember that we check linearity for all continuous variables included in the model. Let's try an example using age in the CHD dataset. Luckily, we already have a categorical version of age, so we can just use that. If we didn't already have this variable, we would need to categorize the continuous age variable to check this assumption. So we'll first calculate the mean value of y for each category of age. And this is equivalent to calculating the proportion of CHD in each category. We'll then calculate the log odds of CHD for each age category, and then plot the logit values against the median of the categories. So what can we say about linearity with this example? Is the relationship between age and the log odds of CHD linear? The relationship looks pretty linear at the higher ages, but it appears to be nonlinear at lower ages. So what can we do about this? Should we use age as a continuous variable? This wouldn't be a good idea because this is nonlinear with the log odds of CHD. One solution is that we could instead use a categorical version of age, and we could consider combining the lower age categories together if we think these aren't too different from each other in terms of effect on CHD. Let's try the same process with weight instead of age. Again, we already have the weight category variable calculated for us. So what do you think? What can we say about linearity here? It looks more like a dichotomy. So those greater than 170 pounds appear to have higher odds of CHD than those less than 170 pounds. So we should probably use a binary weight variable of greater than 170 versus less than 170 pounds. I guess that's why the binary weight variable was in the dataset in the first place. So rather than using the model that we currently have, we would instead want to use a model that includes categorical age and binary weight variables. But for the sake of example, let's say that the linearity assumption was met for the continuous age and weight variables. How would we calculate the probability of CHD for a smoker of age 50 who weighs 200 pounds and a non-smoker of age 30 who weighs 130 pounds? For a smoker of age 50 who weighs 200 pounds, we write out the full logistic regression equation and multiply the smoke coefficient by 1, since 1 indicates smoking status equals yes. We multiply the age coefficient by 50 and the weight coefficient by 200. And this gives us a log odds of negative 1.6. We then use the formula to convert the log odds to a probability. This tells us that there is a 16.8% probability of CHD for a smoker of age 50 who weighs 200 pounds. We followed the same process for a non-smoker of age 30 who weighs 130 pounds. But we multiplied the smoke coefficient by 0, the age coefficient by 30, and the weight coefficient by 130. This gives us a predicted probability of CHD of 0.8%. In the next tutorial, we're going to discuss why and when we use Poisson regression. We'll talk about events, counts, incidence, and rates. We'll go over how to fit a Poisson regression model and how to interpret output, check for confounding and effect modification, and how to compare nested models with Poisson regression.
Thanks for watching our video. Stick around, guys, because we got lots more.